Fire safety training is an important part of safety in the workplace. Employers must train employees about fire hazards that exist in the workplace, how to prevent fires, and what to do in the event one occurs. Now, by the end of this course, you're going to be able to identify fire hazards, know the proper way to evacuate safely in the event of a fire, and be able to identify fire extinguishers and how to use them properly. So let's get started. Fire safety in the workplace is important for the safety of employees. To ensure employee safety, it is the employer's responsibility to train employees to identify fire hazards. Approximately 6,000 fires occur in the workplace each year in the United States. Quite often, these fires occur because employees have not been properly trained to identify the causes of workplace fires. Now, this lack of awareness can lead to serious injury from severe burns, exposure, and smoke inhalation, and can even cause death. Arson, smoking materials, wiring and appliances, and improper storage of hazardous materials are all the major causes of fires in the workplace. Should be kept locked after business hours. Outdoor areas around the building, especially alleys and loading docks, should be well lit and kept clear of combustibles. Now make sure that dust, paper, and spilled flammable or combustible materials are cleaned, contained, and disposed of properly. Smoking is a fire hazard. Smokers must adhere to worksite rules. Now, smoking is allowed, and it should be allowed in designated areas only. In areas where smoking is permitted, large ashtrays that will not tip over must be used. When emptying an ashtray, make sure the contents are cold because anything hot that comes in contact with flammable materials could cause a fire to spark. So be sure that no one leaves smoldering cigarettes on furniture or in waste baskets. You also want to make sure to turn off or unplug all unnecessary appliances, including coffee makers, at the end of each workday. Be careful not to overload outlets. Inspect and replace any broken or cracked electrical cords with properly functioning, undamaged cords. Trash, open fire doors, blocked stairways, and poorly stored hazardous materials. Being unprepared and having poor safety practices are among the most common contributors to fire hazards in the workplace. Alarms and signs must be maintained so they are fully functioning. Safety placards and signs are important to communicate hazards to workers. They let employees know what types of materials are present so they can govern themselves accordingly. Never block an exit with boxes, tools, or other items that can act as an obstruction to an egress. All right, let's see what you've retained so far. Which of the following is a practice that does not create a fire hazard in the workplace? Is it A, garbage cans are emptied once every other week? B, a coffee maker is left on overnight so it automatically brews at 7 a.m.? C, employees who smoke can smoke at a picnic table where there are large ashtrays? Or D, loading dock lighting is turned off after business hours? Well, obviously the correct answer is C. Employees who smoke can smoke at a picnic table where there are large ashtrays. If smoking is allowed on the worksite, it should be permitted only in the designated areas where there are large ashtrays that will not tip over. Emptying garbage cans only once every other week means that trash will accumulate, which is a fire hazard. Coffee makers and other appliances should be turned off or unplugged at the end of each workday. And then finally, outdoor areas around the building, such as alleys and loading docks, should be well lit to prevent arson. Every employee must be familiar with their facility's fire and life safety systems. Employees must know what type of emergency systems their worksite or building has in place, along with their location and use. Now, these emergency systems may include manual pull alarms, smoke detectors, exit doors and stairwells, sprinklers, fire extinguishers, fire alarm monitoring services, voice alarms, and fire doors. Every workplace must have a sufficient number of exits available that are properly located to allow everyone the opportunity to escape the facility quickly and safely. Some things that must be considered are the type and height of the structure, the number of occupants, available fire protection, and the type of industry. An emergency exit should never be obstructed or locked when employees are present. However, a delay in the opening of a fire exit is permitted when an approved fire alarm system is tied into the fire exit door design. All exit routes from a facility must be clear and must display an exit sign. If fire extinguishers are present, there must be an extinguisher use program integrated into the site safety training. The program will provide employees with the proper knowledge of extinguisher use. Now, if employers require employees to learn the proper use of the extinguisher, they're required to provide hands-on training. Fire extinguishers are divided into 5 different categories. Class A extinguishers are for the typical combustible materials like paper, wood, and plastic. The numerical rating listed on Class A extinguishers represents the amount of water they can hold and the amount of fire it is capable of extinguishing. Their geometric symbol is a green triangle. Class B extinguishers are for the flammable or combustible liquids, such as gasoline, kerosene, grease, and oil. The numerical rating for Class B extinguishers represents the approximate number of square feet of fire they are capable of extinguishing. Their geometric symbol is a red square. Class C extinguishers are for electrical equipment such as appliances, wiring, circuit breakers, and outlets. Never use water to extinguish Class C fires. There's a risk of electrical shock. Class C extinguishers do not have a numerical rating. The C classification means the extinguisher agent is non-conductive. Their geometric symbol is a blue circle. Class D fire extinguishers are commonly found in a chemical laboratory. They're for fires that involve combustible metals, such as magnesium, titanium, potassium, and sodium. Class D fire extinguishers do not have a numerical rating, nor do they have multi-purpose ratings. Their geometric symbol is a yellow decagon. Class K fire extinguishers are for fires that involve cooking oils, trans fats, or fats in cooking appliances that are typically found in restaurants and cafeteria kitchens. Their geometric symbol is a black hexagon. Water extinguishers are suitable for ordinary combustibles only, such as wood, cloth, or rubber. And you should never use a water extinguisher on a grease or electrical fire because the flames will spread and make the fire even bigger. Water extinguishers are filled with water and are typically pressurized with air. Remember, water extinguishers can be very dangerous if used for the wrong situation. Trained and experienced employees should fight the fire only if they are sure it contains ordinary combustible materials. Dry chemical extinguishers come in a variety of types and are suitable for ordinary combustibles, flammable liquids, and flammable gases. Now, these are filled with either a foam or powder and are pressurized with nitrogen. Dry chemical extinguishers leave a mildly corrosive residue which must be cleaned immediately to prevent any damage to the materials. CO2 extinguishers are used for flammable liquids and gases. The pressure in these extinguishers is so high that it's not unusual for bits of dry ice to shoot out the nozzle. Now, they do not work well in ordinary combustibles because they may not be able to displace enough oxygen to put the fire out, causing it to reignite and even blow particles and pieces of paper. This extinguisher works well in electrical fires that involve electronic equipment such as a computer, stereo, or TV. Fixed fire extinguishing systems throughout the workplace are among the most reliable firefighting tools. These systems detect fires, sound an alarm, and then send water to the fire and heat. In order to meet OSHA standards, when a fire extinguishing system is down for service, employers must temporarily substitute a group of trained employees to act as fire watch to respond to fire emergencies. Employers must also ensure that the fire watch is included in the fire prevention plan and the emergency action plan, and post signs and placards for systems that may use chemical agents that are health hazards. Now, OSHA requires emergency action plans to include a description of exit routes and procedures, the accounting of all evacuated employees, procedures for evacuating disabled employees, and the evacuation of employees who stay behind to shut down critical plant equipment. Additionally, it requires an employee alarm system throughout the workplace that includes voice communication or sounds signals such as bells, whistles, or horns. Emergency training. Previewing the emergency plan with new employees and reviewing the emergency plan with all employees whenever the plan is modified is also required. A fire prevention plan is a written plan that implements safety policies to prevent a fire that endangers lives and workplace operation. OSHA standards require that fire prevention plans include plan availability for employee review, housekeeping procedures for storage and cleanup of flammable materials and flammable waste, instructions on how to handle and package flammable waste, procedures for controlling workplace ignition sources, instructions for cleaning and maintenance of equipment that produce heat and require storage of flammables away from such equipment, and information on potential fire hazards. Let's see if you've been paying attention. What type of fire extinguisher should be used for a fire on a circuit breaker? Is it A, Class A extinguisher, B, Class B extinguisher, C, Class C extinguisher, D, Class D extinguisher, or E, Class K extinguishers? The correct answer is C, Class C extinguishers. Now, use Class C extinguishers for electrical equipment fires. This includes fires due to appliances, wiring, circuit breakers, and outlets. Class A extinguishers are for putting out fires related to typical combustible materials, like paper or wood. Class B extinguishers should be used for fires with flammable or combustible liquids, such as gasoline or kerosene. Class D extinguishers eliminate fires related to combustible materials and metals like magnesium or titanium. Class K extinguishers are for fires involving cooking oils, trans fats, or fats in cooking appliances. Safety from fire hazards is a very serious matter. It requires planning and proper training to be prepared if a fire occurs at a workplace, plant, or site. Employers have a responsibility to train their employees in fire safety for their specific industry to avoid any life-threatening incidents. Employees are responsible for learning the training materials and applying it appropriately in the workplace to ensure a safe environment. Employees must report safety concerns so that the employer can record and address any issues. If these general rules are followed, then proper steps to train employees in fire safety have been taken and preventative measures have been put in place.
In the workplace, there may be jobs with particular tasks that require extending and reaching or some other type of overhead work. Repeating this type of task over long periods of time may cause injury to employees. This is where ergonomics comes into play. What exactly is ergonomics? Ergonomics is defined as fitting a job to a person. It is concerned with posture and movement of the body and environmental factors present when a task is being performed. When the rules of ergonomics are applied to tasks like extending and reaching, the result will be enhanced employee performance without the risk of injury. Employers have the responsibility of providing safe workplaces for employees. To help with this, the Occupational Safety and Health Administration, or OSHA, has created ergonomics program guidelines for various industries from meatpacking plants to nursing homes to retail grocery stores. In this course, we are going to talk about ergonomics in the workplace. By the end of the course, you will be able to define ergonomics, identify risk factors for musculoskeletal disorders, explain the benefits of using a proactive approach to ergonomics in the workplace, and discuss the elements of an effective ergonomic process. The main focus of ergonomics in the workplace is improving the design of work activities to fit people. The purpose is to provide an environment that is conducive to maximum productivity at minimal physiological or health costs to the worker. In order to do this, ergonomics takes three things into account: the capabilities of the employees, the limitations of the employees, and the requirements of the job. By considering each of these, there will be a reduction in the risk of injury. When job tasks do not adhere to the principles of ergonomics, injuries can occur, such as musculoskeletal disorders, which are also referred to as MSDs. MSDs affect the muscles, nerves, and tendons. Work-related MSDs are amongst the leading causes of lost workday injuries and illnesses. In 2011, the Bureau of Labor Statistics, or BLS, revealed that there were 380,820 MSD cases in 2011, which made up for 33% of all cases involving worker injury and illnesses that year. According to the BLS, industries with the highest MSD rates include healthcare, transportation, warehousing, retail, wholesale trade, and construction. Employees of various industries and occupations are exposed to the MSD risk factors at work. These factors include heavy lifting, bending over, reaching overhead, pushing and pulling heavy loads, working in awkward body postures, and performing the same or similar tasks repetitively. Exposure to these MSD risk factors increases an employee's chance of injury. It is important to note that there are risk factors that are not related to work that may have an impact on the employee's vulnerability to MSD risks on the job. These factors include physical conditioning, medical conditions like obesity, diabetes, and arthritis, pregnancy, hand-intensive hobbies, and psychological or social workplace stress. The bottom line is that employers are responsible for providing a safe and healthful working environment for their employees. In the workplace, the number and severity of MSDs resulting from physical overexertion as well as their associated costs can be greatly reduced by applying ergonomic concepts. The best approach to ergonomics in the workplace is a proactive one. A proactive approach to ergonomics emphasizes the prevention of work-related injuries and disorders by recognizing, anticipating, and minimizing risk factors in the planning phase of new work or workplace designs. It creates operations where the appropriate choice and use of tools and equipment, job methods, workstation setup, and materials do not create unnecessary stress or strain on employees. This approach can also prevent additional costs involved in the redesigning of work processes later down the road. In other words, it is often more feasible to minimize risk factors before they occur. For this approach to be effective, designers must be trained on the proper ergonomics information and its framework for minimizing risk. Design makers strategizing new work process should have a working knowledge of the rules of ergonomics that will contribute to the minimization or elimination of risks. Design strategies should have an emphasis on matching job requirements to the capabilities and limitations of employees. For example, tasks that require heavy lifting materials can be simplified with the use of mechanical devices, which would reduce the need for lifting. So, a proactive approach would be to integrate this process into the tasks of the job. Other design aspects should be considered, like load design and layout of the workplace, which would take into consideration the ease of access when using mechanical aids to eliminate unnecessary lifting by an employee. Regardless of whether you are planning the design of new work tasks or improving existing ones, there are specific components of the ergonomic process you should consider. Implementing an ergonomic process has been proven to be effective in reducing the risk of developing MSDs in diverse industries as construction, food processing, office jobs, healthcare, beverage delivery, and warehousing. There are several key elements of this process. First, you must identify existing or potential ergonomic problems. To help with this, you should encourage early reporting of MSD symptoms. Early reporting is another key element of the ergonomic process. Early reporting can accelerate the job assessment and improvement process, helping to prevent or reduce the progression of symptoms, the development of serious injuries, and subsequent lost time claims. Once ergonomic problems are identified, you must then implement solutions to control them, which is another key element of the ergonomic process. Other elements to consider include providing management support, involving workers, providing training, and evaluating process. We'll look at more of these elements next. The first element of the ergonomic process we are discussing is identifying and assessing ergonomic problems in the workplace. If you already have work tasks in place, check for existing ergonomic problems. OSHA's Injury and Illness Recording and Reporting Regulation, 29 CFR Part 1904, requires employers to record and report work-related fatalities, injuries, and illnesses. So identifying existing problems can be achieved by reviewing the company's OSHA 300 injury and illness logs, 301 reports, workers' compensation records, worker reports of problems, first aid logs, accident and near-miss investigation reports, and insurance company reports. Be sure to encourage early reporting of ergonomic-related injuries, as this is important to the success of the ergonomic process. The goal of this effort is to properly assess, diagnose, and treat MSDs. Early reporting, diagnosis, and intervention can limit injury severity, improve the effectiveness of treatment, minimize the likelihood of disability or permanent damage, and reduce workers' compensation claims. It also reinforces worker training on recognizing MSD symptoms and allows for proper medical evaluations for diagnosis, treatment, and follow-up care. This information also allows the employer to correctly identify work areas or specific tasks where injuries frequently occur or are most severe. Such information helps direct the activities of the ergonomic team as well as to guide healthcare providers in making return to work and light-duty work decisions. The information provides a mechanism to track and trend MSD injuries and enables assessment of the effectiveness of work changes. One way that ergonomic problems can be identified is through observation and review. This forward-looking approach, which should be used in combination with the review of injury and illness records, allows you to be proactive in identifying potential ergonomic issues that have gone unnoticed or resulted from facility changes before resulting in MSDs. Observations of workplace conditions and work processes, ergonomic job analysis, workplace surveys, and worker interviews are common methods for identifying ergonomics-related injury risks so that employers can eliminate or control them as early as possible. Employers should also conduct scheduled periodic reviews of the facility, specific workstation designs and work practices, and the overall production process. During observations and reviews, employers and employees should be on the lookout for risk factors. Risk factors of MSD injury depend on work positions and postures, how often the task is performed, the level of required effort, and how long the task lasts. One risk factor that may lead to the development of MSDs is exerting excessive force, for example, lifting heavy objects, pulling heavy loads, or maintaining control of equipment or tools. Performing the same or a similar task repetitively, such as performing the same motion or series of motions continuously or frequently for an extended period of time, is a risk factor. In addition to working in awkward postures or being in the same posture for long periods of time. An example of this might be using positions that place stress on the body, such as prolonged or repetitive reaching above shoulder height, or kneeling, squatting, or twisting the torso while lifting. Localized pressure to a body part, like pressing the body or part of the body, such as the hand against hard or sharp edges, or using the hand as a hammer, is also a risk factor. Cold temperatures in combination with any of these risk factors may also increase the potential for MSDs to develop. For example, many of the operations in meatpacking and poultry processing occur when a chilled product or in a cold environment. Combined exposure to several risk factors will often place workers at a higher risk for MSDs than does exposure to any one risk factor. In addition to watching for these risk factors, employers should also pay attention to whether workers are modifying their tools, equipment, or work area, shaking their arms and hands, rolling their shoulders, and bringing products such as back belts or wrist braces into the workplace. These behaviors can signify that workers are experiencing ergonomic issues. Talk with employees and review their work to see if any risk factors for MSDs are present. Workers can identify and provide important information about hazards in their workplaces. Their opinions and suggestions for change also are valuable. All right, let's see what you've learned. Which of the following would not have an impact on an employee's vulnerability to MSDs? A. Twisting the torso while lifting. B. Diabetes. C. Repetitive reaching above shoulder height. D. Social workplace stress. E. All of these are risk factors. The correct answer is E. All of these are risk factors. Risk factors of MSD injury depend on work positions and postures, how often the task is performed, the level of required effort, and how long the task lasts. Placing stress on the body by working in an awkward posture is a risk. This would include twisting the torso while lifting and repetitive reaching above shoulder height. Diabetes and social workplace stress are also risk factors. Though they are not related to work, they may have an impact on an employee's vulnerability to MSD risks on the job. Once ergonomic hazards are identified, solutions to control them must be implemented. Solution development is a key part of the ergonomic process, and there are many possible solutions that can be put in place to reduce, control, or eliminate workplace MSDs. Conducting an in-depth ergonomic job analysis can help identify solutions to prevent MSDs. An ergonomic job hazard analysis is a technique that focuses on job tasks as a way to identify hazards before they occur. It focuses on relationship between the worker, the task, the tools, and the work environment. To reduce the danger of ergonomic-related injuries, work tasks should be designed to limit exposure to ergonomic risk factors. Engineering controls must be used wherever feasible and are nearly always more desirable than other methods. Engineering controls have to do with the design of the work environment and job itself so that hazards are eliminated or controlled. Administrative or work practice controls may be appropriate in cases where engineering controls cannot be implemented or when different procedures are needed after implementation of engineering controls. Administrative or work practice controls have to do with the company's general workplace rules and other operation-specific rules and procedures. Personal protection like back or abdominal belts or braces have also limited effectiveness when dealing with ergonomic hazards. Many industries have successfully implemented ergonomic solutions in their facilities as a way to address their workers' MSD injury risks. These interventions have included modifying existing equipment, making changes in work practices, and purchasing new ergonomic-friendly tools and other devices to assist in the production process. Making these changes has reduced physical demands, eliminated unnecessary movements, lowered injury rates and their associated workers' compensation costs, and reduced employee turnover. In many cases, work efficiency and productivity have increased as well. Simple, low-cost solutions are nearly always available to solve ergonomic-related risks and problems. Not all ergonomics-related risks and problems can be resolved by easy or low-cost solutions, but you'd be surprised at how many can, if we just try. Other key elements of the ergonomics process include management support, worker involvement, training, and progress evaluation. Let's take a look at each of these elements. First, let's look at what it means for management to provide support. A strong commitment by management is critical to the overall success of an ergonomic process. Management should define clear goals and objectives for the ergonomic process, discuss them with workers, assign responsibilities to designated staff members, and communicate clearly with the workforce. Another element of an ergonomic process is worker involvement, a participatory ergonomic approach where workers are directly involved in worksite assessments, solution development, and implementation is the essence of a successful ergonomic process. Workers can identify and provide important information about hazards in their workplaces. They can also assist in the ergonomic process by voicing their concerns and suggestions for reducing exposure to risk factors and by evaluating the changes made as a result of an ergonomic assessment. Healthcare professionals are also important ergonomic team members. They help injured workers recover more quickly and return to their jobs with appropriate restrictions and less risk for re-injury. It is necessary that these professionals are knowledgeable about the operations and work practices within the specific industry. Their knowledge will allow them to assist the injured worker during the healing process and in post-injury work placement. Training is another important element in the ergonomic process. It ensures that workers are aware of ergonomics and its benefits. It also informs them about ergonomics-related concerns in the workplace and ensures they understand the importance of reporting early symptoms of MSDs. Evaluating process is the final vital part of the ergonomic process. Established evaluation and corrective action procedures need to be in place too, so that the effectiveness of the ergonomic process can be periodically assessed. These procedures also ensure continuous improvement in the process and long-term success. As an ergonomic process is first developing, assessments should include determining whether goals set for the ergonomic process have been met and determining the success of the implemented ergonomic solutions. All right, let's see what you've retained. Employees at a worksite must perform heavy lifting above shoulder height as a task for their jobs. Which of the following options are good ways for employers to limit employee exposure to ergonomic risk factors associated with this task? A. Provide back braces to workers. B. Alternate the task between different employees. C. Keep the worksite at a cold temperature to prevent employees from overheating. D. Modify the equipment used so that employees do not have to lift above shoulder height. And E. Have a healthcare professional monitor the task to ensure injury does not occur. The correct answers are B. Alternate the task between different employees, and D. Modify the equipment used so that employees do not have to lift above shoulder height. Modifying the equipment used is an example of an engineering control. This is the most desirable way to reduce ergonomic risks. Alternating the task between different employees is a good example of an administrative and work practice control. Providing canvas gloves to workers is a personal protective equipment control. However, while these may provide abrasion resistance when handling materials, gloves do not protect against ergonomic injury. Keeping the worksite at a cold temperature is not an effective way to reduce ergonomic risk factors. In fact, cold temperatures actually increase the potential for MSDs to develop. Having a healthcare professional monitor the task does not necessarily reduce the potential for injury, especially if no other controls are put in place. In this course, we defined ergonomics as fitting a job to a person. The purpose of ergonomics in the workplace is to provide an environment that is conducive to maximum productivity at minimal cost to the worker by identifying the capabilities of the employees, the limitations of the employees, and the requirements of the job. We've seen that when job tasks do not adhere to the principles of ergonomics, injuries can occur, such as MSDs that affect the muscles, nerves, and tendons. Employees of nearly every industry and occupation are exposed to MSD risk factors at work, as we've discussed, some more than others, but know that ergonomic-related problems in the workplace are becoming more and more prevalent. A proactive approach to ergonomics is best because it emphasizes the prevention of work-related injuries and disorders by recognizing, anticipating, and minimizing risk factors in the planning phase of new approaches to work or workplace designs. Ergonomic-related problems can be reduced greatly by adopting and implementing the ergonomic process. The important elements of the ergonomic process include identifying problems, encouraging early reporting of MSD symptoms, implementing solutions to control hazards, providing management support, involving workers, providing training, and evaluating progress. We discussed how to identify ergonomics-related problems in the workplace by reviewing company records and encouraging early reporting of MSD symptoms. Taking a proactive observation and review approach can also help to identify ergonomic hazards. Risk factors of MSDs to watch for include exertion, excessive force, or performance of the same or similar tasks repetitively. Finally, we've discussed the various ways to control ergonomics hazards, in particular by conducting an in-depth ergonomic job analysis where solutions to prevent injuries can be identified. Solutions can take the shape of engineering controls and administrative or work practice controls. Electricity is all around us. We use it to make coffee in the morning, to heat up lunch, and to watch our favorite television programming at night. We also use electricity to do our jobs. Some people have to work directly with electricity, such as engineers or electricians. Other people have indirect contact with electricity, like construction workers, office workers, or salespeople. Regardless of the job, we must all be cognizant of electrical safety. Every day, an average of one worker is electrocuted on the job. Not only can electricity cause death, but it can also cause serious injury from shock, burns, and falls. In addition, electricity is also one of the most common causes of fires in the workplace, and it can cause explosions. To prevent injury and death from electrical sources, the Occupational Safety and Health Administration, known as OSHA, has created electrical safety standards to which workers must adhere. There are specific standards for the construction and maritime industries. However, in this course, we are going to look at the general industry standards. By the end of this course, you will be able to explain how electricity works and identify the 4 main types of injuries that may result from electrical contact. You will also be able to describe the 3 types of electrical hazards that may be encountered at the worksite and name warning signs that indicate their existence. In addition, you will be able to discuss methods of protection from electrical hazards and identify safety training requirements for employees who work with electrical equipment. Before we dive into electrical safety, let's talk about how electricity works. First, I want you to imagine a water faucet. When you turn it on, you expect water to come out. In order for that to happen, 3 things must be in place. There has to be a source of water, a force to make the water flow, and a way for the water to be transported. In this case, a reservoir is the source of water, and a pump is what forces the water to flow. When water flows, its method of transportation is pipes, up until the water reaches the faucet. In some ways, an electrical light switch on a wall is not unlike the water faucet. When you flip the switch on, you expect the lights to turn on. For that to happen, you must have a source of electricity, a force to make it flow, and a way for it to be transported to your light fixture. To better understand how your electric light switch works, let's break down some key terminology. Starting with electricity. Electricity is a form of energy created from charged particles. Consumers, and in this case, us and our light switch, get access to electricity through a power plant. The power plant creates an electric current. Current is the movement or flow of electrical charge, and it is measured in amperes. There must then be an electrical force to move the current. This electrical force only exists when there is a difference in charge between 2 points. We call this force voltage, which is measured in volts. In our example, a generator at the power plant provides the voltage that makes the electricity flow. In addition to having voltage, there must be little opposition to current flow, or in other words, there can be little resistance. Getting back to our example, the electrical current from the power plant is transported through wires. Wires are what we call conductors. Conductors are substances like metal that have little resistance to electricity. This lack of resistance allows electricity to flow through the conductive wires. If you've ever dealt with wires, you know they are often not metal to touch. Rather, they are covered with insulated material. Insulators are substances like wood, rubber, glass, and bakelite that have a high resistance to electricity. In other words, insulators prevent the flow of electrical currents. A wire covered in an insulated substance prevents an electric current from shocking a person who may come in contact with it. Dry skin has a fairly high resistance. However, if skin is moist, resistance drops significantly, making it a good conductor. Though pure water isn't a conductor, impurities like salt and acid, which are both present in perspiration, make it a conductor. So we have our source of electricity, the power plant. The current is transported through conductive wires because of voltage flow created by the generator. When you flip the switch to the on position, you are completing an electrical circuit. An electrical circuit is simply an unbroken path along which electric current flows. Turning the switch on closes the electrical circuit and allows electrical current to flow through the wires to the light so it can power on. Working directly with or near electrical currents puts you at risk for electrical injury. There are 4 main types of electrical injuries. Electrocution, which is death due to electric shock. Electric shock burns and falls. When electrical hazards exist, it is important that we protect people by using the proper precautions. Depending on the hazard, this might be through insulation, guarding, grounding, personal protective equipment, electrical protective devices, and safe work practices. Let's take a closer look at electrical shock. Earlier, we discussed that electricity travels in circuits, normally through a conductor like a wire. Electric shock then occurs when the body becomes a part of that circuit. For the body to become a conductor in a circuit, the body must have 2 contact points, one for the current to enter and one for it to exit. Electrical shock usually happens in one of 3 ways. One situation where shock occurs is when an individual contacts 2 wires of an electrical circuit at the same time, without being in contact with the ground. One of the wires becomes a point of entry for the current, and the other wire becomes a point of exit for the current. Secondly, electrical shock can occur when a person is in contact with the ground and also one wire of an energized circuit. The live wire is the point of entry for the current, and the ground is the point of exit for the current. The third way that electrical shock occurs is when a person is in contact with the ground and also a metallic item that has become energized through a conductor. For example, a break in a tool's wiring insulation can energize the metal part. When a person simultaneously comes in contact with that energized part and the ground, an entry and exit point for the electrical current has been created and shock can occur. The severity of shock depends on the path of current running through the body, the amount of current flowing through the body, and the length of time the body is part of a circuit. It is important to note that just because a person is exposed to an electrical circuit with low voltage does not mean it is a low hazard. In fact, low voltages can be extremely dangerous because, all other factors being equal, the degree of injury increases the longer the body is in contact with the circuit. Even a small current that passes through the heart and lungs is capable of causing severe injury or electrocution. Earlier, we talked about how current is measured in amperes. In addition to amperes, current can be measured in milliamperes. A milliampere is equal to 1/1000th of 1 ampere. If a current is greater than 75 milliamperes, it can cause ventricular fibrillation or a rapid ineffective heartbeat. After a few minutes of ventricular fibrillation, death will occur unless a defibrillator is used. Electrical shock can also result in electrical burns. Electrical burns are the most common type of shock-related non-fatal injury. Burns occur when you touch electrical wiring or equipment that is improperly used or maintained. Burns usually occur on the hands and are a very serious type of injury that requires immediate attention. Electric shock also causes indirect or secondary injuries. One such injury is a fall. Workers in elevated locations who experience a shock can lose their balance and fall, or they may become so frightened or stunned that they jump back into an awkward or unsafe position, also resulting in a fall. Falls can cause serious injury or death. John is working near a live electrical wire that is 5 feet off the ground. He sees a bird fly from a nearby tree and land on the wire. Is it okay for John to come in contact with the wire? Yes or no? The correct answer is no. Electrical shock occurs when a body closes a circuit, allowing current to pass through it. To close a circuit, the body must have two contact points, one for the current to enter and one for it to exit. Without both an entry and exit point, electricity cannot continuously flow and shock would therefore not occur. In John's situation, the electrical wire would be a point of entry for the current, and the ground on which John is standing would be the exit point for the current. John's body would act as a conductor between the electrical wire and the ground. The reason that the bird is not injured is because it has contact with only one point, the wire. Electricity must have a completed circuit to flow, with both an entry and exit point. In order to prevent electrical injury, it is important that we first identify the types of hazards that exist. At the worksite, there are three main types of electrical hazards. These are inadequate wiring, overloads, and improper grounding. I'll give you a brief overview of each now, but we'll go over them in further detail later in the course. Something is considered inadequately wired when the electrical current is too much for the conductor being used. Overloads occur when there are too many devices plugged into a circuit. Improper grounding means that even though procedures were placed to de-energize an object, that object remains energized. If people come in contact with that object, they will be shocked. Now, let's look at the conditions in which these hazards occur. Electrical accidents are caused by a combination of three factors: unsafe equipment and/or installation, an unsafe environment, and unsafe work practices. If you are at a work site, watch for clues that electrical hazards exist. These include tripped circuit breakers or blown fuses, warm tools, wires, cords, connections, or junction boxes, a circuit shut off by a ground fault circuit interrupter, which we'll talk about later, and worn or frayed insulation around wire or connection. Electrical injury in the workplace occurs from three main hazards: inadequate wiring, overloads, and improper grounding. In this segment, we are going to look at inadequate wiring and overloads. We'll also identify some ways to prevent these types of hazards. First, let's discuss inadequate wiring. Such a hazard exists when a conductor is too small to safely carry a current. An example would be, say you are using a portable tool with an extension cord. If that extension cord has a wire that is too small for the tool will draw more current than the cord can handle. This will cause overheating and a possible fire. To prevent wiring hazards, a wire gauge should be used to ensure the proper wire size is used in the circuit. Wire gauges identify how large a wire is, and thus the amount of current the wire can safely carry. Another main cause of electrical injury in the workplace is overloaded circuits. When you plug too many devices into a circuit and the safe amount of current is exceeded, an overload occurs. The result is that the current heats the wires to a very high temperature, which may cause a fire. Sometimes wire insulation will melt and result in arcing. Electric arcs are formed when a current jumps a gap in a circuit through normally non-conductive material like air. This too can cause a fire, even inside a wall. In order to protect against hazards like these, electrical protective devices must be used. Electrical protective devices shut off dangerous electricity flow and include fuses, circuit breakers, and ground fault circuit interrupters. Fuses and circuit breakers are overcurrent devices. They are designed to protect equipment and facilities, and in doing so, they also provide considerable protection against shock to people. Both of these devices have current ratings that tell how much current the fuse or breaker can safely handle. If the current exceeds the rating of the device, the fuse or circuit breaker will break the circuit to eliminate the hazard. Fuses break the circuit by melting. This leaves the circuit open, so current will no longer flow. A melted fuse cannot be used again. Circuit breakers break the circuit by what is called tripping. When a circuit breaker is tripped, a switch within the breaker opens the electric circuit, so current will no longer flow, thus eliminating the hazard. Circuit breakers can be reused. If the breaker or fuse has too high of a current rating for the wires they are meant to protect, an overload in the circuit will not be detected and the current will not be shut off. Injury may result in this instance, so it is important to be aware of the current ratings. Likewise, a circuit breaker could be the right rating for the circuit itself, but not for the smaller wire extension cord being used. If that cord is too small to safely carry a current, the circuit breaker would not be tripped, which could cause overheating and fire. A circuit with improper overcurrent protection devices or one with no overcurrent protection device is a serious hazard. Another type of electrical protective device is a ground fault circuit interrupter, or GFCI. Where fuses and circuit breakers protect equipment, GFCIs protect people. This device protects people from dangerous shock caused by ground fault. Ground fault occurs when there is a break, a leak, or an imbalance in a circuit. The electrical current essentially takes a different, unintended path to the ground, such as through a person's body. GFCIs check that the current going to an electrical device is the same amount of current returning from the device along the electrical path. If there is a 5 milliampere difference or more in the amount of current going to the device and the amount returning from the device, the GFCI shuts off the flow of electricity in as little as 1/40th of a second. This protects the user from dangerous shock. Improper grounding is one of 3 main causes of electrical injury in the workplace. In fact, some of the most frequently violated OSHA standards are related to grounding hazards. What exactly is grounding? Grounding is a process where a conductive connection is formed in order to neutralize the charge of an object. This connection forms between a charged object and a ground. A ground has a voltage of 0. When a charged object, such as a live wire, comes in contact with a ground, such as the earth, the charge is neutralized. Grounding is often used to help prevent a person from electrical shock in the event that electrical insulation fails. It also prevents the buildup of static electricity, which could cause a fire or an explosion under the right circumstances. Say you are handling metal parts of an electrical wiring system, like switch plates or ceiling light fixtures. If these parts are properly grounded, they will be at 0 volts relative to the ground. This means that if your body completes the circuit between the metal parts and the ground, there will be no risk for shock. Remember, without voltage, there is no electrical force to push the current. OSHA requires 2 kinds of grounds. First, there must be a service or system ground. This type of ground is primarily designed to protect machines, tools, and insulation against damage. In a service or system ground, one wire, called the neutral conductor or grounded conductor, is grounded. In an ordinary low-voltage circuit, this is a white or gray wire that is grounded at the generator or transformer and again at the service entrance of a building. The other type of ground is the equipment ground. This enhances worker protection and must be furnished by providing another path from the tool or machine through which current can flow to the ground. This safeguards the equipment operator if a malfunction causes metal parts of the equipment to become energized. In this segment of the course, we are going to look at some of OSHA's specific electrical requirements for various hazards. First, let's discuss overhead power lines. Many people don't realize that these are usually not insulated, so protective measures must be taken. If the overhead wires are not guarded or insulated, whoever owns them must de-energize and ground them. Workers using ladders or scaffolds must pay careful attention when working near overhead power lines and should use fiberglass instead of metal ladders. Workers need to be specially trained to work safely near overhead power lines at the required minimum clearance distances. Personal protective equipment, or PPE, must be worn for protection. PPE may consist of rubber insulating gloves, hoods, sleeves, matting, blankets, line hose, and industrial protective helmets. OSHA also has requirements for grounding paths. Any path to ground circuits, equipment, and enclosures must be permanent and continuous. Handheld electrical tools can also pose danger to workers due to their continuous contact with their hands, so OSHA has created specific standards for protection. For instance, power drills use 30 times the current, which can kill a person. For adequate protection, tools must have a 3-wire cord with ground and be plugged into a grounded receptacle or be double insulated or powered by a low-voltage isolation transformer. In addition, live parts of electrical equipment operating at 50 volts or more must be properly guarded against accidental contact. This is achieved through approved cabinets or enclosures, location, or permanent partitions so they are accessible only to qualified persons or through elevation of 8 feet or more above the floor or working surface. Guarded locations must be marked with conspicuous warning signs. If there is a chance that the live parts of electrical equipment can be exposed and cause physical damage, they must be enclosed or guarded. Cabinets, boxes, and fittings also must adhere to OSHA standards. Junction boxes, pull boxes, and fittings must have approved covers. Unused openings in cabinets, boxes, and fittings must be closed with no missing knockouts or partially punched openings. Additionally, flexible cords have to be properly protected to avoid hazards such as shocks, burns, or fire. Flexible cords are more vulnerable than fixed wiring and should not be used if one of the recognized wiring methods can be used instead. Damage to flexible cords can be caused by aging, door or window edges, staples or fasteners, abrasion from adjacent materials, and activities in the area. Let's look at some examples of uses of flexible cords. Flexible cords are prohibited from acting as substitutes for fixed wiring. They must not run through walls, ceilings, floors, doors, or windows, and they must not be concealed behind or attached to building surfaces. Flexible cords can, however, be used for pendant or fixture wiring, for portable lamps, tools, or other appliances, for stationary equipment, and for temporary wiring. Temporary electrical installations of more than 600 volts may be used only during periods of tests, experiments, emergencies, or construction-like activities. Temporary electrical power and lighting installations of 600 volts or less may be used only for experimental or development work, during emergencies, for remodeling or maintenance, and for repair of buildings, structures, or equipment, and similar activities. If temporary wiring is used for the purpose of Christmas decorative lighting, carnivals, or other similar purposes, it cannot be installed for longer than 90 days. Once the purpose for which the temporary wiring was installed is fulfilled, the wiring must be removed immediately. If it is not removed, this could constitute a serious electrical violation. Employees must be properly trained on safe work practices before they can work with electrical equipment. One topic the training must include is de-energizing. This is a process of ensuring that the electrical equipment is off and cannot accidentally or unexpectedly start, which can cause severe injury or even death. All electric equipment must be de-energized before it can be inspected or repairs be made. The training must also provide workers information on using electric tools that are in good repair, using good judgment when working near energized lines, and using appropriate PPE. A worker has plugged several devices into a circuit. The worker supervisor notices this and asks that a reusable electrical hazard protection method be put in place to prevent circuit overload. Which of the following electrical protective devices should the worker use? A. Fuse. B. Circuit breaker. C. Ground fault circuit interrupter. And D. Wire gauge. The correct answer is B, a circuit breaker. Plugging too many devices into a circuit can cause an overload, which may result in fire. An overloaded circuit will trip a circuit breaker and stop current from flowing. A circuit breaker can be reused, unlike a fuse. A fuse will melt to stop the current flow. A ground fault circuit interrupter, or GFCI, protects people from shock caused by ground fault, which occurs when there is a break, a leak, or an imbalance in a circuit. A wire gauge is used to prevent wiring hazards by identifying how large a wire is and thus the amount of current the wire can safely carry. In this course, we discussed electrical safety for workers. We explained how electricity works by dissecting what happens when you turn a light switch on in a room. We also identified the four main types of injuries that may result from contact with electricity, including electrocution, electric shock, burns, and falls. Then, we identified electrical hazards. There are three main types of electrical hazards that may be encountered at the worksite: inadequate wiring, overloads, and improper grounding. We examined how each of these hazards occur and identified warning signs of their existence. We also identified ways to protect against them, including the use of electrical protective devices like fuses and circuit breakers. We also reviewed OSHA requirements for certain circumstances. One such requirement has to do with overhead power lines. Since these types of lines are usually not insulated, there are specific steps that must be followed to ensure workers are protected from them. We also talked about how to properly use handheld electric tools, how to effectively guard live parts, and the correct and incorrect uses of flexible cords. Finally, we discussed electrical safety training requirements. For workers who deal with electrical equipment, there are explicit topics that need to be addressed in training. This includes conducting equipment de-energizing processes, using electric tools that are in good repair, and wearing appropriate personal protective equipment. Imagine the possibility of losing your fingers or having an arm crushed by an improperly guarded machine. Not a pleasant thought, right? There are several ways that you can be injured when working with machinery, and many of them can be horrifying. Each year, unguarded or improperly guarded machines cause 18,000 amputations, lacerations, crushing injuries, and abrasions. They also cause more than 800 deaths a year. These instances can be prevented by using the right safeguards. The Occupational Safety and Health Administration, or OSHA, has developed several standards to help us make sure we do just that. The rule of thumb to remember is that any machine part, function, or process that may cause injury must be safeguarded. So, when the operation of a machine can injure the operator or other workers, we must eliminate or control the hazard. In this course, we are going to discuss machine guarding. We'll look at what causes machine accidents and the specific machinery parts that can pose hazards to operators. We'll discuss requirements for safeguards and identity, the 5 methods of machine safeguarding with examples of each. In addition, we'll talk about the different machine safety responsibilities for managers, supervisors, and employees. Finally, we'll look at the key components that need to be included in machine operator safety training. Machine accidents are caused by a variety of reasons. Accidents often happen when workers attempt to clear a machine jammed with parts of materials. Accidents can even occur when workers reach into a machine that is not jammed. Often these accidents happen because the machine is not properly or sufficiently guarded. Accidents can also happen if workers fail to use lockout tagout, which are the procedures to disable machinery or equipment in order to prevent the release of hazardous energy. Sometimes, injuries occur when unauthorized persons conduct maintenance on or otherwise use machines. Other times, missing or loose machine guards can be the source of injury. Now that you know the main causes of machine accidents, let's talk about where they happen. Mechanical hazards occur in three places: the point of operation, any moving part of the machine, and pinch points. The point of operation is the area where the work is performed. This would be where the machine cutting, shaping, boring, or other operation takes place on the material. This area must be properly guarded. Mechanical hazards are also caused by moving parts on the machine. That means any reciprocating, rotating, or transverse moving parts such as flywheels, pulleys, belts, couplings, chains, cranks, or gears can potentially cause injury. In addition, feed mechanisms and auxiliary parts of the machine can also be hazardous. The third area where mechanical hazards occur are pinch points. These develop when two machine parts move together, with at least one of those moving in a rotary or circular motion. They occur where the machine parts move toward each other or where one part moves past a stationary object. There are three main types of pinch points. Let's take a closer look at each. The first type occurs when parts rotate in opposite directions while their axles are parallel to each other. If these parts come in contact with each other, a pinch point has been produced. If these parts are in close proximity to each other, the stock fed between the rolls produces pinch points. This is common on machinery with intermeshing gears and rotating cylinders. Another type of pinch point takes place between rotating and tangentially moving parts, such as a chain and sprocket, a rack and pinion, or the point of contact between a power transmission belt and its pulley. Finally, pinch points can occur between rotating and fixed parts that create a shearing, crushing, or abrading action. This might be spoked hand wheels or flywheels, screw conveyors, or the periphery of an abrasive wheel and an incorrectly adjusted work rest. We've identified why machine accidents happen and the parts of a machine where hazards can occur. In order to protect against these, safeguards must be put in place. For something to be a proper safeguard, it has to fulfill a few requirements. First, it must prevent contact. A good safeguarding system eliminates the possibility of a worker's clothing or body from coming in contact with a machine's hazardous moving parts. Next, a safeguard must be secure. It must be firmly secured to the machine and not easily removed. Guards and safety devices need to be made of durable material that will withstand the conditions of normal use. Another requirement for safeguards is that they protect from falling objects. They must ensure that objects won't be able to fall into a machine's moving parts and then cause injury. For example, say a small tool is dropped into a cycling machine that was not safeguarded from falling objects. The tool could easily become a projectile that could strike and injure someone. The next requirement is that safeguards create no new hazards. They mustn't have any shear points, jagged edges, or unfinished surfaces which can cause lacerations. A safeguard with any of these pretty much defeats its own purpose. If a guard has a sharp edge, it must be rolled or bolted in such a way that the sharp edge is no longer a hazard. Additionally, safeguards must not create interferences. In other words, a safeguard must not prevent a worker or machine from performing the intended job quickly and comfortably. If a safeguard does not do this, then it is more likely to be overridden or even completely disregarded. Proper safeguarding can actually enhance work efficiency by relieving the operator's apprehensions about injury. The final requirement for safeguards is that they allow safe lubrication. If at all possible, the machine should be lubricated without having to remove the safeguard. Locating oil reservoirs outside the guard with a line leading to the lubrication point will reduce the need for workers to enter the hazardous area. So, those are all the requirements safeguards must meet. Now, let's look at some of the methods of safeguarding. There are 5 main methods: guards, devices, location or distance, feeding and ejection methods, and miscellaneous aids. I'm going to list a few examples of each now, but we'll go over some of them in more detail later in the course. Guards can be fixed, interlocked, adjustable, or self-adjusting. Devices can be presence sensing, pullback, or restraint. Safety controls such as tripwire cable or two-hand control and gates are also types of devices. Feeding and ejection methods of machine safeguarding can be automatic and or semi-automatic feed and ejection. Robots can also be used as an alternative. Miscellaneous aids include awareness barriers, protective shields, and hand-feeding tools. A new machine is installed with a guard. The guard is securely in place and prevents anyone from contacting the machine's hazardous moving parts. Though one edge is sharp, the guard is placed in a way that will not slow workers down or make them uncomfortable. It also provides protection from falling objects and allows for safe machine lubrication. The safeguard on this machine is okay for use. True or false? The correct answer is False. The guard described does not meet all of the requirements for safeguards. While the guard protects, contact is secure, protects from falling objects, creates no interference, and allows safe lubrication, it is missing one requirement. It must create no new hazards. The guard has a shear point, which could cause lacerations on workers. In order to remedy this new hazard so all safeguard requirements have been met, the sharp edge should be rolled or bolted in such a way that the hazard is eliminated. We've identified the methods of safeguarding. Now, let's take a closer look at a few types of guards. A fixed guard is the preferred type of guard. It is a permanent part of the machine that provides a barrier, such as a door or a cover. As a general rule, a power transmission apparatus is best protected by fixed guards that enclose the danger area. Interlock guards are designed in such a way that anytime they are opened or removed, the tripping mechanism and/or power automatically shuts off or disengages. When this happens, the machine cannot cycle or be started until the guard is back in place. An interlocked guard might use electrical, mechanical, hydraulic, or pneumatic power, or it might use a combination of these. Interlocks must not prevent inching by remote control if required, and replacing the guard must not automatically restart the machine. Another type of guard is the adjustable guard. This type provides an adjustable barrier in order to facilitate a variety of production operations. Adjustable guards are useful because they allow flexibility in accommodating various sizes of stock. However, since they require adjustment, they are subject to human error and should be used with caution. The final type of guard we are going to look at is the self-adjusting guard. These guards provide a barrier that moves according to the size of the stock entering the danger area. Thus, the self-adjusting guards eliminate the potential for human error associated with adjustable guards. Now, let's take a look at examples of another type of safeguard devices. First, we'll discuss pullback devices. Pullback devices are primarily used on machines with stroking action. Here's how they work. Pullback devices use a series of cables that are attached to the operator's hands, wrists, and/or arms. These cables allow the operator to access the point of operation when the slide or ram is up. When the slide or ram begins to descend, the pullback device withdraws the operator's hands, preventing injury. Another type of device is the restraint device. Cables or straps are attached to the operator's hands at a fixed point. The cables or straps are adjusted to a length that lets the operator's hands travel within a predetermined safe area for the work to be done. Oftentimes, hand-feeding tools are necessary if the operation involves placing material into the danger area. Safety controls are another type of device. There are different kinds of safety controls, including tripwire cables, two-hand controls, and two-hand trips. Safety tripwire cables allow workers to quickly stop machinery by pulling the cables. The cables are placed around the perimeter or near the danger area of the machine. They have to be placed so the operator can reach the cable. To restart the machine, tripwire cables must be reset manually. Another safety control device are two-hand controls. In order to activate machines that have this kind of device installed, the operator has to put constant, concurrent pressure on control buttons. These buttons are required to be at a safe distance from the danger area while the machine completes the closing cycle, thereby protecting the operator's hands. On power presses, this kind of control requires a part revolution clutch, brake, and brake monitor. A similar device, known as a two-hand trip, is used on machines equipped with full revolution clutches. This device requires concurrent application of both of the operator's control buttons to activate the machine cycle, after which the hands are free. The trips have to be placed far enough from the point of operation so it is impossible for the operators to move their hands from the trip buttons onto the point of operation before the first half of the cycle is completed. This prevents the operator's hands from accidentally being placed in the danger area prior to the slide, ram, or blade reaching the full down position. The final type of device we are going to look at are gates. A gate is a movable barrier that protects the operator at the point of operation before the machine cycle can be started. The gate has to be fully closed in order for the machine to function. Another potential application of this type of device is where the gate is a component of a perimeter safeguarding system. Here, the gate may provide protection not only to the operator, but to pedestrian traffic as well. Another main method of machine safeguarding is through location or distance. The basic premise is that the machine or its dangerous moving parts are located so they are not accessible or do not otherwise present a hazard to a worker during normal operation. This allows the worker to maintain a safe distance from the danger area. There are two main approaches to take in location or distance safeguarding. One approach is to locate the machine's operating controls at a safe distance. This works well if there is no reason for the operator to tend to the machine or the material when the machine is in use. Another approach is through the facility's design. In this method, the facility is designed so there is a wall between the machine and the workers. This way, they are protected from hazards while the machine is in use. Enclosure walls and fences can also restrict access to machines. An alternate solution is to locate dangerous parts of a machine high enough so they are out of normal reach of any worker. Another method of machine safeguarding is through proper feeding and ejection methods. Before we look at some of these methods in more detail, let's first review how machines work. We know that machines typically have specific operations they perform on certain materials. A feeding method is how the operator supplies those materials to the machine. An ejection method is how the machine supplies the operated on materials. For feeding and ejection methods to be considered properly safeguarded, they must protect workers by minimizing or eliminating direct contact with the machinery. Many feeding and ejection methods do not require operators to place their hands in the danger area at all. In some cases, no operator involvement is necessary after the machine is set up. Other times, operators use feeding mechanisms to assist in manually feeding materials to the machine. Properly designed ejection methods do not require operator involvement after the machine starts to function. Keep in mind that just because you are using feeding and ejection mechanisms, the need for other safeguards has not been eliminated. So you'll still have to use guards and other devices to protect against hazards that haven't been eliminated. Let's take a closer look at one type of feeding method, the automatic feed. An automatic feed provides a mechanism for getting the material to the point of operation by eliminating the need for the operator to be in the danger area during the process. The operator's exposure to hazards are thereby reduced. Alternately, feeding and ejection methods can sometimes be achieved with robots. Robots are machines that perform tasks such as unloading stock, assembling parts, or transferring objects. Robots are best used with high production processes that require repeated routines. The benefit is that robots prevent hazards to employees. However, please note that robots may create their own hazards. The employer needs to conduct a comprehensive operational safety and health hazard analysis to identify hazards the robots may create, and then implement an effective safeguarding system that is fully responsive to these situations. One of the most common guard techniques is to use perimeter guarding with interlocked gates. The final method of machine safeguarding includes miscellaneous aids. These are not meant to provide complete protection from machine hazards. Rather, miscellaneous aids provide the operator with an extra margin of safety. One example of a miscellaneous aid is a protective shield. Keep in mind that protective shields do not provide complete protection. Protective shields guard workers against flying particles, splashes, cutting oils, or coolants. Another example of miscellaneous aids is holding tools. Holding tools are used to place or remove stock in the danger area. Holding tools must never be used instead of other safeguards. Instead, they should act as supplementals. Now that we have a good grasp on the types of safeguards, let's look at how OSHA requires specific types of equipment to be guarded. Many work sites have fans. When the periphery of the blades is less than 7 feet above the floor or working level, the blades must be guarded. The guard openings must be no larger than 1/2 inch. OSHA also has specific standards for guarding abrasive wheel machinery, such as offhand grinding machines. Offhand grinding is a form of rough grinding without regard to the surface finish. The work itself is usually held in the operator's hand and placed against a moving abrasive wheel. For this type of operation, work rests must always be adjusted closely to the wheel. The opening between the two must not exceed 1/8 inch. This prevents the work from being jabbed between the wheel and the rest, which may result in wheel breakage. In addition, the distance between the wheel periphery and the adjustable tongue must never exceed 1/4 inch. Finally, let's take a look at OSHA standards for a power transmission apparatus. This can include shafting, flywheels, pulleys, belts, or chain drives. If this power transmission apparatus is less than 7 feet from the floor or working platform, it must be guarded. Machine safety is everyone's responsibility. This includes management, supervisors, and employees. Management has one main responsibility, and that is to ensure that all machinery is properly guarded. Supervisors must ensure machine guards remain in place and are functional. If there are machine guard deficiencies, supervisors are responsible for immediately correcting them. Supervisors also need to train employees on specific guard rules in areas where they work. Employees then have the responsibility of successfully completing the training. In addition, employees must never remove guards unless the machinery is locked and tagged. If there are problems with machine guards, employees need to report those to the supervisors immediately. Finally, if a machine does not have a guard in place or if there is a problem with the guard, employees must not operate the equipment until the guard is properly in place. A few moments ago, we touched on safeguard training for employees. We know that machine operators must receive appropriate training so they can safely use machines. But what exactly must this training include? First, operators must be trained on the hazards associated with each machine. They must be taught how safeguards provide protection and the hazards for which they are intended. They must also learn how and why to use safeguards, in addition to how and when safeguards can be removed and by whom. Finally, training must include information on what to do if a safeguard is damaged, missing, or unable to provide adequate protection. Identify the type of safeguard described below. When this safeguard is opened or removed, the tripping mechanism and/or power automatically shuts off or disengages, and the machine cannot cycle or be started until this is back in place. Is it A, safety tripwire cables, B, two-hand trip, C, pullback device, or D, interlocked guard? The correct answer is D, interlocked guard. Safety tripwire cables are located around the perimeter of a danger area so the operator can easily reach the cable to stop the machine. A two-hand trip requires concurrent application of both the operator's control buttons to activate the machine cycle. This device is typically used with machines equipped with full revolution clutches. A pullback device utilizes a series of cables attached to the operator's hands, wrists, and/or arms. Access to the point of operation is allowed when the slide or ram is up. When the slide or ram begins to descend, the pullback device withdraws the operator's hands. In this course, we discussed using machine guarding to prevent injury to workers. As I said earlier, the rule of thumb is to always remember that any machine part, function, or process that may cause injury must be safeguarded. We identify the causes of injury, such as missing or loose machine guards, and where mechanical hazards occur on machines, including the point of operation, any moving part of the machine, and pinch points. We looked at the requirements for safeguards, such as preventing the worker's body or clothing from contacting hazardous moving parts. We also explained and listed examples of the 5 main methods of machine guarding: guards, devices, location and distance, feeding and dejection methods, and miscellaneous aids. Finally, we looked at the responsibilities of managers, supervisors, and employees regarding machine safety. One of the responsibilities of supervisors is to provide training for machine operators. This training has to include several key elements, including how and why to use safeguards,